in as we start. My name is Tim Conway. I work for the SANS Institute, specifically in the Industrial Control Systems curriculum, and instructor, author, and curriculum lead in that area. Today we are joined by Reed Whiteman and Kate Vita, both from the organization Dragos. But for those who are joining, we usually do a really good job of kind of identifying when we're having analyst-sponsored webcasts or vendor-sponsored webcasts, as we want people to know when they're connecting and when they may be hearing more about a company's product or solutions and specifically join for that reason. However, this webcast is not one of those. This isn't an analyst-sponsored or a vendor-sponsored. We just happen to have two people from industry that are leaders in this space that are going to be joining us and talking through the topic of the Ripple20 vulnerabilities. And this is more of a industry focused talk. It's not specific to a company or a product or a solution. It's for those who are members of our community forum. When different events happen, like the Trisis attack or Ukraine 2015 or something of extreme interest within the industrial control system space, we often put together resources and defense use cases and white papers and make those resources available to the industry through our forums or through webcasts, and that is what this webcast will be focused on. Both Reed and Kate work in this space specifically, and kind of in their day jobs, we couldn't find two better folks to come and talk about the Ripple20 vulnerabilities and answer some of the questions of really focusing on what people in the industrial control system community need to know about this and what it means. So Reed is a Dragos senior vulnerability researcher, analyzing publicly disclosed vulnerabilities and determining the public reporting is accurate and really kind of what it means for the industrial control system community. Kate is a senior vulnerability analyst for the Dragos intelligence team. She analyzes public advisories for accuracy, understanding, and correction to feed intelligence and the Dragos platform. She performs vulnerability research and assessments of software and hardware as needed. For those who've seen some of the Dragos reports, looking at some of the vulnerabilities being reported and tracked in different industry documents or certs, kind of some of the research that both Kate and Reed have performed in the past, looking at which ones of those kind of vulnerabilities are significant, which ones are accurate. Same thing on the patching side. So really just both of these individuals, we couldn't be more blessed to have them come in and talk about what this means to asset owners and operators as things like this come out, no different than the Urgent 11 vulnerabilities specific to the real-time OS of VxWorks. And people started to try to understand, where do we have that in our deployed assets? And what does it mean from a risk perspective? And what does our response need to look like? The same questions are being asked of Ripple20, and it's harder to find, harder to identify, harder to go through inventory and fixed assets and determine what it means for asset owners and operators. I'm not going to take any more time. I'm going to turn this straight over to Reed and let them begin answering those questions that the industry is sort of asking and looking to them.
Great, thanks, Tim. Yeah, so I am Reed Whiteman. I'm a principal vulnerability analyst here. I've gotten most of my work, I would say, in the industrial security space has been focused on embedded systems. So back in the day, I kind of got into the industrial space by joining the company Schweitzer Engineering Labs, where I did a lot of negative testing of digital protective relays, looking for issues in the hardware, issues in firmware, issues in communications protocols. I do have a really fancy home lab that has, it turns out, a lot of equipment in it that's impacted by the Ripple20 vulnerabilities. And it's kind of interesting because I have a huge range of equipment that is, some of it is, quite unsupported at this point by the vendors. Some of the equipment that I have in my home range is, sort of end of life by the vendor. I have them looking right now at one of the UPSs that I won't be talking about, but which has a no longer supported Ethernet card in it, which is impacted by the Ripple20 vulns. And I know that that network card is never going to see a firmware update, for example. And I guess I'll turn it over to Kate to say a little bit about her lab.
Sure. My name is Kate Vita. I'm a senior vulnerability analyst here at Dragos. My background is mostly in system administration and network administration. I was formerly a pen tester for a while. And yeah, my home lab is growing. I've got, I think, 3 devices here that we're going to be talking about in regards to Ripple20. But otherwise, I'm just excited because it's growing. And I think I can change the slide. Nope. Okay, cool. So what you need to know, first, if you haven't read it yet, you should probably check out the JSOF white paper. You can find it on their website at jsof-tech.com/Ripple20. Today, we're going to go over some of the key takeaways of the following, like devices impacted, the prevention strategy, mitigation tactics, and any of the research implications that it means, for you guys, our community. Maybe I can change it. I don't think it's working. Oh, maybe. All right. So maybe this doesn't work. Can you advance? Okay, cool. So we're going to go over the vulnerabilities that were identified in the Treck TCP IP stack, and it's very difficult to read these. Cool. So we've got the JSOF research paper, which was actually published last month, about a month ago. It was released with a demo, and in the demo they show several devices plugged into, I believe, a UPS, and they shut them all down, the processes stop, and none of their devices work. In their white paper, they highlight 2 of the 19 vulnerabilities that they consider the Ripple20 vulnerabilities, and one of which is a remote code execution vulnerability, and the other is an information leak. So there's probably going to be more information on the rest of the vulnerabilities, I believe, in tomorrow's Black Hat talk. I think it's at 11 o'clock. Probably local time at Black Hat tomorrow. So check that out. If you paid for Black Hat, obviously you won't want to miss that one. Otherwise, I'm not sure how it's going to transpire to the rest of the community afterwards, but they should have more information on that. What's fascinating though is the vendor coordination that they've done. So you can actually go to their website and they'll have a list of several vendors which show which devices are affected, and more importantly, how they're affected, whether they're actually a denial of service or a remote code execution or not affected at all by some of the vulnerabilities. They actually, in a lot of websites, they link to each of the advisories, and it's pretty cool how well they've broken down what each device is actually vulnerable to. I think I might be fighting the control for this all day. Either way, where we see these devices, these are embedded systems, which are usually just plugged into or attached to another device that has no native IP stack. So they use the Treck IP stack. So it's not very easy to detect, and you can actually go through that advisory and see some of the fixed dates, just how much they vary, some going back quite a ways. But all of them have a different CPU and some completely overall device architectures. So there's a lot to look at from all of these, and it's not necessarily easy. It's not one size fits all type of vulnerability.
Yeah, and it's kind of funny, you see a lot of these advisories and they say it's like the Treck TCP IP stack, which is kind of a misnomer. I kind of laugh about it because I'm like, well, it's like an IP stack that happens to have UDP. If you read the advisory, there are vulnerabilities in the DHCP client. So it's DHCP software that's incorporated with this quote unquote TCP IP stack. But the big thing is there's 3 big bugs that they kind of highlight right at the top of the Ripple20 advisory that are memory corruption bugs. And some of those have kind of nuanced outcomes that we'll probably be hearing about, over the months ahead. But then there are a whole bunch of more minor bugs, which are really integer underflows that don't seem like they can be used to actually get code execution or real memory corruption. There's a bunch of bugs that are like out of bound memory reads and data leaks. It's like things in packet length fields that are kind of sound at least vaguely similar to issues like Heartbleed, where you can probably send a fragmented packet that claims it's too big, and you'll get some ICMP data that happens to be just leftover data from a device in the response message. But yeah, like Kate was saying, these impacts are going to vary a lot by devices, and we'll be walking through a bunch of devices to look at exactly what some of those impacts will be. And some of those bugs, if you look through that Ripple20 advisory, some of these bugs were actually fixed in the Treck stack a long time ago. I want to say there are a couple of CVEs that were fixed actually in the official Treck builds going back to like 2007, 2009, 2012, 2014. So not all devices are going to be vulnerable to all bugs, specifically because, hey, maybe the vendor kept a support contract and was actually incorporating these old fixes in the Treck stack into their firmware updates. At least we can see from the JSOF blog post that the newest or the biggest bugs are reported, at least for now, to be affecting all versions of the Treck stack up to the latest. Yeah, we'll have to take a look in the future and see exactly how right that is, but we will see. So there's a lot of different types of device that are actually impacted by, or that incorporate the IP stack, and so are going to be vulnerable. In the industrial space, we're really concerned with things like digital protective relays, programmable logic controllers, especially their network cards, remote terminal units, even UPSs, I think, are pretty important, and that's going to actually be part of JSOF's live demo tomorrow. We'll be talking about it a little bit. And then there's a lot of kind of ancillary equipment that happens to incorporate the stack. In our lab, we'll be talking about actually 5 different devices. We only list 4 here. We got a last minute addition, I think on Sunday or Monday, right, Kate? I think you got another piece of hardware that we started tearing down. But we have these devices in our various home labs. I know I have a couple of these APC SmartUPSs with network cards. I think Kate has one of these Y ME 9210s. And I know that Digi makes another version of that module that actually has an Ethernet port on it. This is a wireless version. We bought it really specifically because JSOF published kind of a full, well, not quite full, but mostly full RCE proof of concept, or at least information about how to achieve RCE on that device. We also recently picked up a SCADAPack 32. And I happen to have one of these digital protective relays from ABB in my lab. I've had it for a couple of years and just haven't done much with it, but it's been nice to dust it off. And I think, Kate, you picked up, what is it, an Opto 22? Is that right?
Yeah, one of the snap pack switches.
Sure.
Yeah.
Okay. Yeah. So we'll also be talking about that. That'll be a 5th device. I wanted to talk a little bit about kind of a general PLC architecture. And if you watched a couple of weeks ago, I was giving a presentation with another of my colleagues here at Dragos for SANS, and we were talking about kind of threat intelligence and how to look at vulnerability advisories as they come out. And one of the things I was pointing to was that PLCs, especially older PLCs, and it's the older ones that are, in my opinion, more likely to be affected by the Ripple20 vulnerabilities. Those older PLCs were designed kind of for a different era. And it was, a lot of these PLCs started out as being serially connected devices. They were connected to an RS-485 serial network in your plant. And the addition of Ethernet networks was kind of a novel concept, in the late 90s, early 2000s. So a lot of vendors kind of looked at the past and looked towards the future and said, we're going to make our PLCs modular. In other words, we'll have this thing have a processing unit with slotted IO cards, and we'll even have slotted communications cards, and that's how we're going to provide our Ethernet connectivity. So a lot of PLCs, when you think about them architecturally, look a little like this, where you have a network card with its own processor that's communicating on some backplane, oftentimes via a serial protocol, to the processing unit. So that network card has its own processor, its own operating system, and it is the thing that all the components on your control systems network communicate with when they want to pull data, like, for example, into an OPC server, data historian, human machine interface, that sort of thing. So this is kind of the classic PLC architecture, and we're going to look at a couple of devices and see how they fit in and whether they fit in with this sort of classic PLC architecture. But really the idea with this classic PLC architecture is if we can crash an Ethernet card or even compromise an Ethernet card, it's not going to really affect the processing unit, not directly. We're going to need something else in addition to just popping the network card. So let's dive into our first victim device. This is an APC SmartUPS. And again, I believe JSOF is going to be presenting tomorrow at Black Hat a proof of concept exploit. We didn't, recreate a proof of concept exploit for this or anything. We just decided, hey, let's, we have a couple of these. Let's tear it apart, see exactly how things are laid out inside. So I have a couple of different SmartUPSs with 9630 series Ethernet cards. I believe these are called Network Management Card 2s. I have one 9630 and one 9631, and there's a little bit of difference that I'll try to talk to. But these cards actually run an embedded operating system known as MUCOS. It's actually MUCOS 2 is the operating system, and they have the Treck stack bolted on top of that. And this card, I guess, go over to the next slide here, actually has this processor in the middle of it. And that processor is actually labeled APC, right? It's an ASIC. But I've seen this sort of thing before. I've taken apart a lot of industrial hardware over the years. And one of the devices I looked at years ago, I happened to buy a couple of different hardware revisions. And one of them had, you know, a vendor branded ASIC, and the older version actually had a generic processor on it called an RDC R8800 or 88,000 series or whatever they call it. And I'm suspecting that that's what this is under the hood, but I'm not 100% sure. But what these RDC chips are they're an 80186 CPU. Usually they have like an on-die CAN controller, a couple of on-die serial ports, and a couple of other features that are kind of neat. But what this card has, at least, is this x86-ish processor that communicates with the UPS board. And so it can get status from the UPS, both in terms of, you know, hey, what's the temperature, what's the voltage input, frequency that you're seeing. It can also issue commands to the UPS and turn the UPS off. And it's kind of a lights out management board because you can remotely turn the UPS off. And while the UPS is off, the network card is still powered. So you can still log into it and then go ahead and turn the UPS back on. So it's a little bit like a lights out management for the UPS itself. So this again was the card that I actually picked up a few years ago, and it might be hard to tell on your screen, but it's kind of amusing that there is a little brown wire connecting one of those chips over to the connector plug in the upper right-hand corner of the card. That was on the card when I bought it, and it's actually kind of amusing. That chip that wire is connected to is a CAN transceiver. It's a control area network chip. And that is the method that they use for communicating between the card and the main UPS itself. A little about these cards. They support a lot of different protocols. They support SNMP. They have a BACnet stack installed on this for building automation. They also have a Modbus TCP stack. The interesting thing to me about all of this was that, you know, playing around with the BACnet stack, there are actually control points defined in the BACnet protocol map. You know, they're control objects that let you actually shut off the UPS by design. So if you happen to have one of these devices and you have BACnet enabled, you actually have bigger problems than Ripple20, I think. And some models of UPS, actually the Modbus TCP stack allows you to issue control commands to some models of UPS. None of the ones that I have in my own home have this, but I think if you install this exact card into certain models of matrix UPS and bigger kind of data center UPSs, you can actually use Modbus TCP to write to certain control registers that will turn the UPS off. It's kind of curious that that's only allowed on certain UPS models and not others, given that BACnet can shut my low-end UPSs off, but just kind of something interesting to note. So this is the BACnet configuration. And one of the things I wanted to highlight about the BACnet configuration setup, if you happen to own one of these, is that it lets you set a device communication control password. There's a little password entry box midway down. It's the second to the last setting there. That doesn't have anything to do with actually issuing control commands via BACnet. I'm not actually 100% sure what that's meant to accomplish. BACnet is an unauthenticated protocol. There are a few commands in BACnet that allow you to use authentication, but they're only like a device reboot command, and there's some other informational command that I can't remember off the top of my head that actually can require a password. Generic write commands, and especially read commands, don't require any authentication in the BACnet standard, and they don't require any authentication on this UPS. This is a part of the BACnet map. And again, this is probably small font. If you have a big screen, you should be able to see it though. There are a couple of control points here that let us power off the UPS entirely. as well as to control individual port groups, in other words, outlet ports on the UPS, and they are all labeled as read-write, RW in that read-write field. And this is just an example of using the BACnet discovery tool. It's a free piece of software for communicating BACnet to actually issue a command to that APC or that UPS control BACnet point. One other curiosity about these smart UPSs is that they have a remote monitoring service. And this is where things get kind of weird. We like to talk about industrial Internet of Things, you know, devices that may phone home to some central control service. That's exactly what this remote monitoring service is for. And what's weird about this is that I have two of these network management card 2s. Only one of them actually has this feature on it, and it's the 9631. That one's actually running an older firmware version. I updated my 9630 card to the latest firmware, which I believe is 6.88. That latest firmware, I don't know if it's the firmware that removes this remote monitoring service feature or if it's the 9630 that just doesn't support it. But this service is, you basically can configure your UPS to phone home to a structureon.com server and report its status. So basically it will tell the central service, you know, how the battery health is, what kind of temperatures and power spikes the UPS has been exposed to, so that you can be a bit more proactive with maintenance. This is so that you can get nice email alerts, or so you can log into a central console on the StructureOn website and, you know, figure out what needs to be replaced, what needs maintenance before things go south on you. But this is generally the architecture that this device follows, right? We have on our left side, we actually have our AP9630 network card, and it has the Ethernet port that presents these protocols to the network: BACnet, Modbus TCP, SNMP, their remote monitoring service. And that card is the thing that's vulnerable. Now that card speaks that CAN protocol to the smart UPS itself, which then controls relays that can, you know, shut off your power, which is a bad thing if you're a victim of something like this. But what I think is the important thing here is that crashing that 9630 does not disable UPS protection. If somebody crashes that network card, your UPS will just hum along just fine. It will still protect when there are power spikes. You should also keep in mind, of course, I think the demo that they presented on a video on JSOFT's website is being able to remotely power off the UPS. Well, that's actually a design feature that's built into the BACnet protocol on all models of these controllers. So if you have BACnet enabled, you definitely restrict access to that protocol port. It's UDP 47808. Make sure that only your building management systems can connect up to that service. You know, use ACL, use IP ACLs everywhere you can. And you might want to read through the network management card Modbus map for your specific UPS and see if you have the ability to write via that Modbus protocol. And if you're not using BACnet and not using Modbus, just make sure that they're disabled in your lights out management cards configuration. The kind of challenge, of course, if you do go down the path of exploiting the memory corruption bug on this 9630 is always the so what. You have to figure out how to send those canned commands to the UPS to actually turn it off. I don't think that will be such a challenge. I mean, JSOFT pulled it off. I'm sure if we stick a CAN bus sniffer on here, we can figure out what those commands are. We could also reverse engineer the firmware and figure out what function to call to do that directly. But, you know, it's kind of the important thing I want to say here is, like, before you freak out that all of your UPSs are vulnerable and that someone is going to shut off power in your data centers or even your PLC racks, keep those things in mind, right? That, you know, developing an exploit for this, not the easiest thing in the world, especially a remote code execution exploit. If somebody can crash it, you'll still be mostly protected. And, you know, your bigger priority might be restricting access to those specific protocols. And I think, Kate, this was your fun little toy, right? You want to talk about the 9210 a bit.
Yeah, so this is the Digi Connect Wi ME 9210. And it is a serial converter that you can add to existing infrastructure. what that means is that it kind of relies on the device maker that's using it to actually like modify the firmware and set up any sort of securities they have on their side. The device runs NetOS on an ARM processor, and by default, it opens up this Digi Discovery protocol on UDP 2362. I think also Telnet and FTP were on there as well. But only this device so far that we know of has actually been reported to be vulnerable to this CVE 2020-11-896, which is the RCE vulnerability that JSOF mentioned. We have a huge shout out and thanks to Finite State, their research team, for walking us through this device's firmware and some of the discoveries that they had. We really appreciate that. That was good. I don't know if I can change the slide. All right, there we go, cool. And then here we have one of Reed's pretty diagrams that show us the Ethernet port that controls the device, which also just communicates over serial to the industrial products I/O. And in this, we likely have direct serial access right through the Ethernet port, which is very similar, but somewhat different than the last one. But by default, you can connect to these devices via wireless, and then you can telnet in, which is also pretty easy to figure out. They're pretty simple, small devices, and I'm not exactly sure everywhere that they're deployed, but they're easy enough to get a hold of. Next in my lab, we have the Schneider Electric SCADAPack RTU RTU, which all of the versions of it are affected. The one that I have here in my lab is the 32P4, which runs on SH3 CPU. We weren't actually able to figure out what operating system it is, but we were able to decide and determine that the logic and the Ethernet are on one set of firmware. What was both frustrating and fun for me, you may not be able to see it very well in this picture, but there's a coating on top of all the important chips that I wanted to be able to read, and I wasn't able to scrape off or otherwise see through any creative lighting, which I tried, to actually read some of the chips. So to get around this and to get more information about the architecture for this device, had to look at pictures on the internet, kind of Google dork some of them, and just trying to figure out what kind of chips these actually are, and was later able to validate through the firmware what they are actually. Either way, this might not be something that's normal for most places, like IoT devices or any other embedded systems, but I think it might be quite common in the industrial environments that this coating might be over all your chips and make it really difficult where you have to work for it. But what we were able to determine is that all of this stuff communicates to the Ethernet controller, and in this, we actually have unauthenticated Modbus project access. So anybody who's on this network and can throw Modbus commands to it are able to change the logic of these boards. Let's see what's next. And actually, there is some security, and this is a screenshot of the configurator tool that we were using to configure the device. Has the security lock tab, which even though this is unsupported firmware, it is not supported on this device. It shows up as, can't figure out the security lock. Either way, it looks like this particular one has no actual security functionality. But we think we do list the ports here. So it uses Modbus, which we can access the project logic. It's got the RTU and ASCII versions of it as well that use different ports. And you actually have to reach out to Schneider for the DMP activation, which are on those ports as well. So if you can't really securely lock this yourself, you'll likely have to use like an external firewall or something to actually block these and restrict it to only things that should be accessing and changing the logic of these devices. I think that's the end of mine.
Yep. Yeah, so next up, we were looking at this ABB REF615, which is, and I do see we have a question about network-based scanners and fingerprinters. We actually have a little thing about that with some links towards the end of this talk. There are network-based scanners. I don't know exactly how accurate they're going to be yet, since we've been throwing them at some of our devices and getting questionable results, but we will keep looking at that and seeing if we can improve it. The ABB REF615 is a feeder protection relay, so it's meant to protect, moderate power load devices as well as like small transformers. The CPU in this one is actually a PowerQuick. It's a PowerPC, and we keep talking about what processor is in each of these devices. And so far, we've looked at 4 different devices. Each one has a different CPU type inside, right? I think we had a device with its x86 based, one that was SH3 Renaissance based. We had an ARM processor. Now we've got a PowerPC. It's kind of an interesting data point, just because there are, in order to exploit these things, you have to know what the underlying CPU is so that you can write bytecode instructions to actually that will execute on that CPU. And it's just interesting to see the huge variety of processors in each of these devices. And we really did pick these devices because like, oh, we have these and we see that there are advisories out there. We didn't pick them specifically because they each have a different CPU inside of them. This one's kind of an interesting one that violates our rule because it actually has a separate Ethernet board. And the leftmost picture here shows the back of this device. A lot of digital protective relays are architected a lot like PLCs in that they have slots, and this is so that you can have different I/O options easily. Since some people use these devices as kind of real-time automation controllers, and people use them to protect different types of equipment, so that they need different combinations of analog and digital inputs and outputs, just based on what it is that they want to achieve. Well, the network card in this is slotted. There are these two little thumb screws you can unscrew, you can pull the network card out, but the network card itself has almost nothing on it. This was kind of a surprise to me when I took it apart. The network card just has an Ethernet physical port. It has an Ethernet physical adapter on it, and then it has one little teeny tiny chip on it, and that's it. And that little teeny tiny chip is a PTP, or Precision Time Protocol chip. I guess it just watches the Ethernet frames go across and says, hey, I see a Precision Time Protocol broadcast message. I am going to process that because I am the PTP chip, and I'm just going to let all of the other Ethernet traffic flow through this card to the actual control board that sits inside of the relay deep down in there, and I haven't been able to pull it out yet. But all of those other protocols, Modbus TCP, DNP3, 61850, are going to flow through actually to the main controller processor and get actually parsed there. So this one was interesting to me just because it's like, well, that's where the Treck stack actually lives, is on that main controller board that's really has direct access to the actual I/O. Just kind of an interesting one. So I actually think that just architecturally, looking at the hardware, a device like the REF615 is a little bit more concerning. I worry mostly because the protection logic on this device is uploaded via FTP, and it actually requires a password. And some of us might be chuckling, saying like, okay, great, FTP, that's a plain text protocol, someone can sniff the traffic, and that's true, but still requiring a password is a lot better than a lot of industrial devices do as far as loading any kind of logic into the device. Like most of the devices we've looked at so far in this talk, it's like, okay, well, I guess Kate actually hasn't talked about the Opto 22 yet, has she? But things like the SCADAPack is more typical, where you can upload new logic to the SCADAPack without any kind of authentication. So this one was kind of cool, and my hat's off to ABB for actually having security in the device. What worries me about the Treck vulnerabilities is like, okay, crashing the device might mean that we lose actually our protection logic, since that one CPU is running both the IP stack and is probably doing some of the I/O commands for controlling when relays, or when circuit breakers are going to trip, and when other things are going to be brought offline due to power surges. And the memory leaks here could actually be useful, right? If somebody happens to be logging into an REF615 and we can leak some memory from it, we might be able to retrieve that password, and we might be able to do it in a way that's remotely done. Obviously we could do some sort of person in the middle attack against someone logging into the FTP server, capture credentials that way. But remote memory leaks would be much more interesting. We don't know if there's any immediate impact from crashing the REF615, but I could see it being bad if it was done as part of a coordinated effort. And what I mean by that is the REF615 is probably going to lose protection while it's crashed, right? In other words, it's not going to be monitoring the grid anymore. If there's a spike in voltage, it may not trip a circuit breaker. That's not going to have an immediate impact on you, right? There's not going to immediately cause damage. But if somebody crashes this and there's a power spike, now you might have, this loss of protection could be something more serious, where, equipment could actually get damaged. We could burn up lines, we could, burn up transformers, that sort of thing. So to me, the REF615, out of the devices we're looking at, is probably one of the more concerning ones for as far as having an actually usable vulnerability to an attacker. And I think this was the late edition that Kate, you just got this like yesterday or something like that.
Sunday. It was yesterday, Sunday. I don't know.
Sure. Yeah.
But even in that time frame, we were kind of able to pick it apart pretty quickly. It has a cold fire CPU, and also the processing is the same for the Ethernet controller as the CPU.
So that's like the 5th different processor type, right? Out of our 5 devices, I think everything has a different processor type. I mean, it's
madness.
Crazy. Yeah, it's crazy, right? Because it's like, it's just a ton of different CPU architectures.
All of which, they're all so fun and unique. Here are the pictures of the board. The middle one's the one that actually has a CPU. Thank goodness I can actually read it. Didn't have to fight that one. And then here's our diagram for that. And this one's a little scary because it actually shows we've got direct memory access over TCP through this Ethernet. So, I mean, it's got other protocols as well, but I mean, who really cares when we can directly access the memory? And it gets better because the tool we use to inspect the device actually tells you what each memory address is for. So it has all the maps for each of the different things. If you want to pull firmware, other information, it's all there. Which is pretty nice, and uses their proprietary, I think I say it here, Opto MMP protocol to run commands to it through reading status and other stuff. So here, actually, this device, through the Opto MMP protocol, you can send a device restart from PowerUp just through that command, which is also going to deny the service to it, which is similar to the vulnerabilities that you'd see with Ripple20. And I think I say which ports. So FTP is actually where it uses to upload firmware. And in this, you actually can add a username and password. By default, it doesn't have one, but you can add it. So definitely check out the security features that go with it. But specifically use the IP filters, because you can actually restrict which actual like IPv4 addresses can actually talk to it. And you need to do that because there's direct memory access otherwise. And I don't think that's, should definitely not have that open to your network in any way. It doesn't make sense. So, oops, I think that's.
Yeah. Yeah, the Opto one was kind of amusing to me because that's actually their term for their Opto MMP protocol. Is like they say it's IEEE 1394, which some people may know as FireWire. It is basically a DMA protocol, and it's just wrapped up in a TCP packet and shipped off to the device. I thought that was really funny, like reading through the data sheets for that, especially since there's actually a huge Opto MMP protocol guide that gives you all the addresses of all of the interesting stuff in their controllers. It's just kind of weird. So again, I think on that Opto 22, it's like, why care about a vulnerability when we can manipulate memory directly on the system using a design feature? This is kind of a summary of, industrial impacts. We like to, in the industrial space, look at loss of view and loss of control. So a lot of these devices, what I'm most concerned with is the fact that we can knock Ethernet boards offline, even if the device is still functioning. Your HMIs and operators may not be able to see what's going on your plant network or even your building, your managed building network. But loss of control can be a little bit harder to quantify. With the SmartUPS, I mean, we see that we have the ability to issue commands to that UPS and turn it off, but that's not really 100%. I mean, there's no proof of concept that's been released, at least publicly at this point. So I'll call that a soft loss. Even if we crash the device, it's still the UPS itself will still be doing protection. The Y ME 9210, it's a lot harder to quantify that device because it is not a control device. It doesn't have any ability to directly control things. It's meant to be installed in some other device. So, we can say that yes, crashing the device or even completely compromising the device means that the attacker can blind your operators or even hide data from your operators, but it's not really possible to tell what kind of loss of control that's going to result in. That's really going to depend on the security of your serial protocol. If you're wise enough to encapsulate authentication and encapsulate some additional security inside of that serial protocol in your device, you'll be well protected. If you're not wise enough to do that, then I would probably call it a soft loss of control. Just because, again, just because you compromise the 9210 does not mean that you have stopped the device from doing its protection function. For the SCADAPack, you know, again, a lot of these are going to be total loss of view just because a lot of these bugs can result in crashes where we can blind our operators at the very least. These devices, of course, you know, we are operating on the main CPU, the last three devices here. You know, the packets are being parsed on the main CPU that does the logic and does the protection by the device. But we also have to think about the fact that at least two of these are insecure by designing, meaning that, you know, there's features in the product that mean that we could totally compromise the device even without the bug. The REF615, of course, is the one that I'm most concerned with, especially since we've seen attacks that take advantage of bugs like this in the past. Specifically, the crash override attack in Ukraine crashed Siemens digital protective relays using a, you know, at the time, public vulnerability, and that could prevent the relay from offering protection, which could be a dangerous situation.
All right, cool. Thanks for advancing that for me. So I'm going to be talking about some of the active scanning. I think a couple people continue to ask about that. We've only really played around with Nmap and recently discovered this one. The link is a little small here, but it should also be at the end slide. But this will basically fingerprint ICMP, figured out as a unique TCP stack, basically whether or not it potentially, I guess it'll say likely, relies on the Treck IP stack. So that one I would say is a little hit or miss. I think I only threw it at a couple of my devices and I think I'm 50%. So it's not completely clear how true, false positive, or, you know, what the rate is. Sorry that it's not that cool.
Yeah, there is a question about that. It's how is the false positive rate? I think when you ran it, it was like it detected one device properly, said one was like maybe Treck. Basically, it said like the ICMP stack looked like Treck and the TCP part did not, or something. Yeah, something like that. I don't know that we even run it against non-Treck devices to see what it answers.
I have not. I've only tried it against the ones that we were.
Yeah, so we don't know exactly what the false positive rate is yet.
I have not used the detection script released by JSOF.
I actually think that Luby Ruffy.
Oh, is that the same one?
I think it is an official JSOF person. Actually, I think if you look at that GitHub page, it'll be like, yes, this is the official JSOF script. I'll have to take a look and see what the deal is with that.
Search for it. And then we've also been using the Nmap OS fingerprinting, which kind of ties into how we would be doing detection strategy.
Yeah, and you know, kind of like figuring out how to actively scan for this. It's like I used to do this stuff a lot like years ago, where, you know, it would be like, all right, let's run Nmap, let's get the actual, you know, results of all of the little malformed TCP packets that Nmap sends, and let's see if we can come up with a way to like passively identify the device. And we're working on that too. I mean, you know, that's something that we'll probably be incorporating, and sorry, this is the plug, we'll be incorporating into our platform. We do have a detection platform specifically that we would be looking for not only like vulnerable devices, but also potential exploitation. And there are some like Suricata signatures that are already out there. CertCC published a couple of different Suricata/snort rules. I have to see if they actually work with snort or not, or how much modification they would require. I know Corelight published some Zeek rules for identifying, you know, potential exploitation and that sort of thing. And finally, it's like, okay, if you passively identify or even actively think you've identified something with a Treck stack, you really do have to go to the firmware and start reverse engineering the firmware. Unless the vendor has published their own advisory and already gone down this path. But you really do need to look through the firmware to see, like, is this thing really vulnerable? And the reason for that is that vendors do some weird stuff sometimes, right? This is an IP stack. And for example, if you're running a DCS controller, distributed control system controller, that happens to have the Treck stack inside of it for some reason, the vendor is going to make a lot of modifications to that stack, right? Because those distributed control systems, a lot of times they rely on weird multicast traffic. So they might even make some modifications to the way that like the basic stack handled some of those incoming packets. And that could actually affect whether or not the device is vulnerable to the issues. So it's really important to go through and verify the vulnerability either via static analysis or even manual testing. And again, shout out to the guys at Finite State because they've been starting down this path of analyzing a lot of firmwares and making some pretty amazing progress as far as telling what's vulnerable and what's not.
There's also another question. Is Ripple20 only an issue for the target machine, i.e. machine that's you're explicitly accessing, or does it also affect devices which are in transit like a router?
Routers typically aren't going to be running the Treck stack. I mean, it's possible that we'll run into one that does, but they are probably going to be running some more robust IP stack, I want to say. So I don't think that those devices are going to be impacted by these vulnerabilities. That said, I mean, some of these things are like kind of weird, old school IP mangling stuff. And it wouldn't really surprise me to see at least some bugs that would overlap with commercial routing products. What's kind of amusing is that, routers and stuff do filter out some weird mangled packets. Like if you run Nmap OS fingerprinting, for example, some of those tests will not pass through a router and even make it to the end device. But we don't have enough details on some of the Ripple20 bugs themselves, since a lot of them haven't really been published yet. Of course, we're independently hunting for them, but it takes time, so we don't actually know. Yeah, so that's my non-answer answer. But the answer is probably not. Yeah, so as far as like prevention strategy, the three major bugs that we were talking about were the first one was the CVE 2020-11896. It's an IP over IP with the fragment flag set on one of the IP layers. One of the other bugs was in some IPv6 processing, and the third kind of big bug that could result in memory corruption and remote code execution was in DNS response processing. The remaining bugs that are, kind of in the category of less severe on the JSOF site, most of those seem to be memory leaks. A couple of them are like integer overflow or integer underflow bugs that can't really result in arbitrary code execution. But a lot of them are memory leaks. And again, in the industrial space, so many of these devices are insecure by design. It's like a memory leak is not super useful. The exception being maybe that one example we looked at, the REF615, which actually had security built into it. I could actually see a memory leak being useful there. But a lot of these bugs also affect protocols that aren't super widely used in the kind of classic industrial space. And I'm talking specifically like DNS. A lot of times industrial devices don't allow DNS outbound from their control systems network. And if they do, they should really restrict it. I've been to a lot of sites back in the day where you would do a pen test or a security assessment from the control systems network. And one of the cute tricks we always did was, okay, let's assume we've compromised a system here on the control LAN. How can we get out? And one of the answers was always DNS tunneling. I would just keep an iodine server running on the internet so that we could connect up to it from inside the control network and show that like, hey, this outbound DNS is actually a big issue. You might want to restrict this. So it's pretty easy if you're running like Windows name servers to, prevent them from forwarding requests for non-internal domains. So if you work for yourcompany.com, you can specify your control systems DNS server that only allows IP lookups within the yourcompany.com domain list. That will go a long way to like helping at least reduce the attack surface from those DNS kind of client attacks. And then the other services, there's DHCP, which is not super widely used in the industrial space. We've seen a ton of devices that are vulnerable to it, to flaws in DHCP processing over the years. I'm thinking especially of Siemens on this one, actually. I know in the last 2 or 3 years, I can think of at least a dozen advisories for Siemens embedded products. It's not to pick on them, it's just that they had a lot of advisories specifically related to DHCP packet processing. And just, preventing these protocols from crossing network boundaries is the most important thing. We did have a question. It was like, can you foresee a way to use Ripple20 vulnerable devices to provide an indirect attack platform to leverage into the larger organization? That's a complicated question. Yes, I can see the use for these, although I will caveat that by saying that it seems that a lot of these bugs are, you know, in order to exploit them, you do have to have some level of access to the control network. And second, I think a lot of the devices, at least in the industrial space, aren't going to have a whole lot that they can do as far as outbound requests. The exception might be this whole DNS issue. If you're allowing outbound DNS, especially if you're allowing arbitrary outbound DNS, then yes, I could see an issue here where you could do some sort of DDoS against name servers or DDoS against whatever server that happens to have port 53 open. But given the kind of restricted nature of a lot of devices, I can't really see it as being super useful. Now, that said, I mean, if you find some common devices that are exposed, for example, on Shodan, that could be a bigger issue. There really aren't that many, for example, APC UPSs that we've been able to find on Shodan, but there may be some other devices that happen to have the Treck stack in them that will have direct internet exposure, and that could be a problem, definitely a problem. But again, you know, to really get the RCE against these devices does require a lot of RE skill. It's not the sort of thing that I think a script kiddie would do. You know, unless there's some monetary gain from running a huge botnet full of DDoS widgets, then I would say maybe not. Let's see, there was another question. There were reports of some medical devices that are vulnerable. Unfortunately, we don't really track medical devices. I mean, we're pretty darn focused on industrial. So I don't know what the impact on those devices would be. You know, some people that would maybe be good to talk to would be folks like Billy Rios over at Whitescope. I know he's done a lot of teardowns of things like medical infusion pumps. And there's some other folks that do a lot of medical device research that just not thinking of their names right now. But yeah, it would be really useful, I think, to look at it. Well, first of all, to see if there's a general device architecture for medical components that kind of mirrors the typical PLC architecture. That would give us a better answer. I simply don't know. I don't look at enough medical equipment to be able to say one way or the other. So there is a silver lining to all this. I mean, it's that, you know, our classic ICS devices are the ones that are, in my opinion, more likely to be affected by the vulnerabilities here. And those are the ones that typically have the separate network card. And they also each have different weird architectures inside, like different processor architectures. And of course, like, owning the network card doesn't get you everything, right? You still have to do a lot of reverse engineering of the controller itself to say, from the network card, what can I do that's bad that will like knock the controller itself offline? The newer ICS devices, I think, are less likely to run the Treck stack, but more likely to try to run both logic or protection and network protocol stack on the same device. The Opto 22 is a great counterexample to that. I'm actually glad we picked it up just for that reason. But it would really surprise me to see vendors like producing a new PLC today running the Treck stack under the hood. It seems like a lot of industrial equipment has kind of gone down the route of running VxWorks rather than running some embedded operating system that doesn't have a native IP stack. Since, you know, it's like, well, if you're designing a new device and you're making this huge architectural change, you might want to reevaluate what operating system you're using as well as what IP stack runs on top of it.
So I guess more good news and silver lining, as so far we haven't actually seen any active exploitation. So no need to panic, even though panicking is probably easy. But these bugs are very similar in nature to the Urgent 11 vulnerabilities, which were released, I think, I think it was last July.
Has it been a year? It feels like it's been 10 years, right?
I'm pretty sure it was July. You know, honestly, wow. Time is a flat circle.
Yeah, I think this Urgent 11 was right before Black Hat last year, I guess, yeah.
Yeah, and I don't think we've seen any active exploitation in that one as well. So I guess not to panic, things can be solved. And on top of that, actually getting an RCE requires a lot of effort because of all the different CPU architectures that we've seen, operating systems, and each thing differs wildly between devices. And I think we've been able to see that even with the small set of devices we have here.
Time is on our side. And like as far as research implications, like this, going back to this APC again, you know, when I see stuff like denial of service and RCE, I always am like, what's the actual impact on the process here? The APC thing was kind of interesting to me just because by design it can shut off, and that's kind of like the demonstration of RCE. The UPS will still function even if we crash that card. But what was really interesting to me was the fact that this kind of back-end communications happens via the control area network protocol. So there are CAN commands going on, you know, on that little ribbon connector that connect the network card to the UPS. And the web interface of that, network management card lets you set a few settings in the UPS, a few protection settings. Like you can specify how high the voltage has to get before the UPS says, this power is no good, I'm going to fail over to battery so that I'm only outputting 120 volts AC. You can also set the low transfer voltage, in other words, how sensitive it is to brownouts. And you know, these when you're changing these settings, it's going to issue some CAN commands to the UPS. I think a great area of research would be like looking at the UPS board itself. Now that we know, like, okay, we can get RCE on this card. Now that we know that, it's like, what can we do with that other protocol? You know, can we, the web interface here is restricting these values, but can we send some additional values to these devices? For example, could we set the high transfer voltage to be below the low transfer voltage, and would the UPS itself actually accept that? Or does it, you know, does it have its own sort of settings, filtering or adjustment inside of the UPS control board? I think that's a cool area of research and something that I'd like to dig into a bit more, you know, in the coming weeks, if JSOF hasn't done it already, and maybe they have. We'll be looking forward to their talk tomorrow. I guess if anybody has questions, you can ask us now in the Q&A window. I don't know that we have microphones turned on for anybody, or you could just email us at intel@dragos.com. And kind of finally, we want to leave these links up for everyone. The JSOF paper is a really great read. Again, I think those guys have done a great job with responsible disclosure, especially because they've been working with a lot of vendors to really determine, you know, not only what's vulnerable, but how bad the vulnerability is. You know, like I said, there's a lot of different dates at play here, a lot of different fixes and partial fixes to this stack over the years. It's kind of nice to see good information being presented by the researchers here, and not like overly sensational, like the sky is falling, kind of everything is vulnerable to RCE all the time talk. The active fingerprinting library that we talked about is there on GitHub. There are also Suricata signatures published by CertCC, and those Zeek rules by Corelight. And again, if anybody has any questions, you can email us, or we'll stick around for a few more minutes.
Thank you both. While we're waiting for any other questions to come in through the Q&A, I'm not gonna lose the opportunity to talk to either one of you over the next 2 minutes. So first is, I have a couple of questions that I'll ask while we're waiting for others. Have you seen general announcements of kind of where this Treck IP stack is in use from the normal list of kind of Siemens, Schneider, GE, SCL, ABB, Rockwell, the kind of group of folks that may have some oddball products or some weird devices outside of their core? Is there anything that should be of, or is of growing concern to either one of you?
We have, so that the JSOF site actually does list a lot of specific devices. I mean, the vendors are doing a pretty good job of putting out their own advisories, and JSOF seems to be doing a good job of tracking those advisories. Nothing too surprising at this point. I mean, like I said, you know, I've been reading through a lot of advisories, mostly with the aim of like, what do I have in my lab? What should I think about buying? But you know, there are, like I said, ABB did publish an advisory which says, for example, the REF615 that we have here is vulnerable. APC, or Schneider Electric, now has published advisories about their UPSs. Eaton's also published advisories about their UPSs. I expect that we'll see more and more as time goes on. I imagine that this is a little bit tricky for some vendors, though. If you follow the industrial vendor world, I mean, it's a lot of acquisitions, right? My UPS says APC all over it. APC got bought by Schneider Electric. So unfortunately for Schneider, this became their problem because they bought, you know, this whole code base that they now have to support that happens to have this vulnerability. Like they may have not even known that their product had this when they bought it, or they may have updated the firmware in the meantime. But yeah, I think it's, you know, it's going to be, as time goes on, we'll see more products come out with announcements that they're actually vulnerable.
Also, one more kind of, we're at the top of the hour and we'll wrap with,
Sure.
with one question. So in your, in the chart where you're kind of looking at the loss of view, loss of control, areas of concern,
yeah,
that we often talk about as kind of the next step of a manipulation of control. Have you thought about any potential to use these vulnerabilities to start modifying data, not just looking at a loss or an unavailability or a drop of service, but a manipulation of data that's moving through these devices?
Sure. Yeah, and that's kind of right, the loss of view. So it's like, can we not just blind operators, but can we actually manipulate what they're seeing so that, for example, the frequency is slipping on the grid, but the operator thinks that everything is a-okay, right? Everything is still running at 60 hertz or 50 hertz, depending on what continent you're on. Is that what you're talking about?
Yeah, exactly.
Yeah. So I mean, in that, even right. I mean, even in the quote unquote good architecture where the network card is separate from the protection logic, yeah, that's a total or complete loss of view, as I like to call it, where the attacker would have the ability to manipulate the view or just completely blind the operator, you know, totally. And yeah, we do make that distinction internally. I think on my slide, I said something like basically everything was like total loss of view or something like that. I'd have to scroll back and look, but yeah, I think that's certainly a concern. We did have another question too about using DOS attacks to take down local control networks. And yeah, I think that's kind of interesting. I mean, I think an attacker at that point has to know your internal network layout pretty darn well. You know, they have to know specifically what IP addresses they want to knock offline on your network. Given a combination of like that, they'd have to know a lot about your network, and B, they'd probably have to be somewhere in your network already to pull off the attack. I'm not 100% sure that it's that useful. But again, it will depend on the device being targeted, right? There's a lot of old, especially like DCS equipment and stuff that's really susceptible to traffic floods. I can imagine, you know, if you get onto like a big turbine control DCS network and start jamming it with traffic, that could be really bad.
All right. Thank you to both of our presenters, Reed and Kate, and to your organization, Dragos, for letting you both come and spend some time with us and share some great information to the ICS community. Definitely thank you to our attendees, especially those who came a half hour early to watch us. And a couple of questions have come through. You can find, if you are interested in obtaining continuing education units for this webcast and any completed webcast that you joined, by logging into your SANS portal, navigate to your account dashboard, then click My Webcasts. You can download your continuing education units on the right-hand side of the page. A copy of the slides and the recording of this webcast will be available for viewing later. You can find it on the SANS webcast registration page. Log into your portal and you can view the slides or the recording of this webcast. Thank you again to everybody for joining. Please enjoy the remainder of your day and stay safe. We will now close the webcast, I think.